My name is María de Rosario Valdespino Mejía. I am a master student at CIDESI, and I'm going to tell you a bit about my work entitled Development and Characterization of Calcium Polymer SILICO-PHOSPHATE Composite Candidates for the Manufacturing of Diabetes Dressing. According to the World Health Organization, there are about 22 million people worldwide with diabetes, where from 12 people, at least one person has it. Diabetes is a chronic degenerative disease that can turn into different complications in the bodies of people who suffer from it. Among which we can find peripheral neuropathy, which affects the photosensitivity, triggering diabetic foot ulcers. It's estimated that at least 6-8% of people with diabetes develop ulcers. Currently, the treatments used to treat diabetic foot ulcer consist of the patches are the intended on proof and the shortening and healing time this condition. But these treatments are costly, non-functional, and size limited. In this sense, material science and engineering has ability for developing a new treatment for these injuries, such as one dressing from biopolymers by new particles that promote a functionality that helps to treatment and cure wounds. For the owner of this warehouse developed composite dressing for biopolymers such as metal, cellulose, and polyvinyl alcohol. These biopolymers have properties such as biocompatibility, absorbability, degradability, and good mechanical properties. They make them ideal for develop or dressing. All the formulation of composite dressing was developed by adding nail particles to the polymer matrix, which are calcium silicophosphate that has been shown to simulate mechanisms that can improve to home regeneration process such as angiogenesis, collagen synthesis, and cell proliferation. The first step of this research involved the synthesis of nail powders, which were fabricated following the methodology of our research group, which consists in a mixture of hydroxyapatite and bioactive glass aspergillus powder using a high-energy mechanical milling. Then a sintering process is performed where the phase is obtained. After sintering, a post-milling process is carried out to homogenize to particle size. Finally, the powder is sized to obtain a particle size below 53 microns. The powder obtained is structurally characterized by X-ray diffraction and laser diffraction to determine the particle size. For the preparation of the polymer membranes, solution of PBA, MIC, and PBA MIC with and without glycerol and agar particles were fabricated. Subsequently, the membranes were manufactured by the place casting method, and the drying and shaping was studied by two methods: convection oven and freeze-down cycles drying, where a physical cross-linking is induced to stabilize the matrix and obtain the polymer membrane. The fabricated membranes were characterized by XRD and C to determine the dispersion and the presence of the ceramic particles in the polymer matrix. Subsequently, a degradation test was carried out to determine the stability of the membranes in terms of mass loss after 5 days, and at the same time the absorption capacity of membranes. After the degradation test, it was found that the metal cellulose membranes with glycerol with and without ceramic particles were completely degraded. So, they were no longer considered for the following tests. Finally, in the order to know the capacity of membranes to trigger biological mechanisms, by activity test was carried out at 6 and 10 days. Subsequently, the mechanical properties of polyvinyl alcohol membranes with glycerol and polyvinyl alcohol with metal cellulose with nagel particles were evaluated by monitoring the maximum stress, the percentage of elongation, and Jones modulus. The result shows the mass of nagel powder particles have a particle size of 84 microns with a distribution for a 1 micron or 34 microns. The readable refinement result confirms the formation of nagel face with 89% face content. Since the conventional oven drying methods promote the entry of the polymer matrix and leads to rapid solvent elimination, causing the effect of malformation in the membranes, which not desirable for application was dressing of this type of membranes. Thanks to the XRD characterized of membranes to points of peaks corresponding to the nagel particles was found, and by seeing was possible to confirm the presence of particles in the polymer matrix when a distribution around the membrane. The degradation test showed that the metal cellulose membranes were not suitable to be used as dressing as they degrade completely after 5 days. However, PBA and PBA-MC with glycerol membranes with and without nagel particles show an absorption percentage above 15, indicating the ability of these membranes to absorb exudates. Mechanical tests showed that the PBA membranes with glycerol with and without nagel particles have very good mechanical properties, especially elongation above 100%, which call for the placement addressing as they are flexi and can be adapted to different wound areas. The bioactivity test shows that the membranes are able to prove the biomineralization mechanisms. In conclusion, we were able to manufacture polymer membranes with very good mechanical and bioactive performance, as well as the ability to absorb exudates, which show the potential of these membranes to be used as one-handly dressing. In the following step of the research, we will continue with development of in vitro and in vivo tests to determine the performance of these membranes and the biological level in the participation of the tissue regeneration mechanisms. Finally, I want to thank the CONACYT for the opportunity of the master scholarship that allowed me to carry out this research.